Hi, I'm Mark Barsamian. In this video, I'll be discussing equivalence relations. This material is from section 8.3 of the book. The corresponding homework is this collection of 7 exercises from section 8.3. So today I'll talk about the definition of equivalence relations and equivalence classes. I'll talk about the relation induced by a partition, and I'll give some examples of equivalence relations. And I'll talk about the partition induced by an equivalence relation. And I'll also talk about what's called congruence modulo D. Stuff from previous sections that will be useful. The idea of disjoint sets. 2 sets are called disjoint if their intersection is empty, if they don't intersect. A collection of sets is called mutually disjoint or pairwise disjoint if, when you look at the intersection of 2 sets that have different indexes, they don't intersect. And a partition of a set A is a collection of non-empty sets that have the property that their union is the set A and they are mutually disjoint sets. In the previous section, section 8.2, we learned about 3 properties that relations may or may not have. The reflexive relation. To say that a relation on a set A is reflexive means that every element of A is related to itself. To say that a relation on a set A is symmetric means that if one element of A is related to a second element of A, then the second element is also related to the first. That's more concisely spoken this way. For all A and B, if A is related to B, then B is related to A. And we talked about the idea of a transitive relation. A relation on a set A is called transitive if, for all A, B, C in set A, if A is related to B and B is related to C, then A is related to C. In this section, 8.3, we're interested in relations that have all 3 of those properties. So that's going to be what's called an equivalence relation. Here I've got a typo. When you say that R is an equivalence relation, what that means is that, well, first of all, you're talking about a relation R that's a relation on a set A. And what it means to say that R is an equivalence relation is that R is reflexive, and R is symmetric, and R is transitive. There's some additional terminology and notation. The equivalence class of little a is denoted this way, little a in square brackets. Now when you use that symbol, little a is an element of set capital A. And what it means is that symbol, bracket, little a, stands for a set. It's the set of all x's in set capital A such that x is related to little a. That's what's called the equivalence class of little a. It's that thing. Example 1 is the relation induced by a partition. So given a partition on a set, the relation induced by the partition is denoted, we're going to denote it by capital R. It's defined to be the relation that behaves this way. We say that x is related to y means this. There's a subset in the partition such that both x and y are in that subset. So there's a theorem that says if you have a set A and you have a partition and you let R be the relation induced by that partition, well then R is reflexive and symmetric and transitive. So in other words, that relation induced by the partition is an equivalence relation. So for example, let A be this set, 0, 1, 2, 3, 4, and let these 3 subsets, A1, A2, and A3, be defined this way. A1 is that set containing 0, 4, A2 is this set containing 1 and 3, and A3 is this set containing 2. Notice that that collection of 3 sets, A1, A2, A3, is a partition of set A. Let's review why that makes sense. Every element of set A is in one of those sets. That is, the union of these 3 sets equals set A. And furthermore, every element of A is in exactly one of these 3 sets. That is, these sets don't overlap. They are pairwise disjoint. These two sets don't intersect, these two sets don't intersect, and these two sets don't intersect. So there are no numbers in set A that reside in more than one of these sets. So those three sets really are a partition of set A. So we can talk about the relation induced by that partition. We're going to give it the name R, and we're going to define it by saying this. X is related to Y means that there's a subset in that partition that X and Y are both in. So that relation R is an equivalence relation. So question A is to write R as a set of ordered pairs. So R is a set of ordered pairs where the left element is a member of set A and the right element is a member of set A. Notice those first four ordered pairs are all ordered pairs where the left element in the ordered pair and the right element of the ordered pair are in set A1. Those next three ordered pairs are built from elements that are in set A2. And the last ordered pair in the relation is the ordered pair made up of elements from set A3. So that's R as a set of ordered pairs. Now we have to illustrate R using a directed graph. So there's a graph of relation R. Notice that R is reflexive because every number has a loop to itself. That's a giveaway that the relation, or that's a sign that the relation is reflexive. We can see that the relation is symmetric because every arrow that goes someplace has an arrow going back the other direction as well. And we can see that the relation is transitive because every segmented path, for instance, this path that goes from 0 to 4 and then back to 0, every segmented path like that has a direct path that does the same thing. Question C, find the equivalence classes. Well, the equivalence class of 0 is, let's go back up and look at the definition. The equivalence class of 0 means the set of all x's in the set A such that x is related to 0. So there are the equivalence classes. Notice, though, that they're not unique. This equivalence class is the exact same as that. The equivalence class is the set. So that's what's behind this question D. What are the distinct equivalence classes? So the distinct equivalence classes, that is the equivalence classes that are sets that are not like any other sets, are just these three. And hey, notice that the distinct equivalence classes are exactly the same sets that were the partition that we started with. Example 2, let X be this set, capital X. Question A says, list the elements of this thing. Remember what that is. That's the power set. And remember that that's the set of all subsets of X. Well, what is the power set? What are the elements? Well, we have to list all the subsets of set X. That's the collection of all possible subsets. Now, notice that this largest subset is actually all of X, and the smallest subset is the empty set, the set that contains no elements. Now, how do I know that I've got all of them? Well, notice that the quick answer I won't talk about much here. We'll talk about this more later in the course. X has 3 elements. 2 cubed is 8. There are 8 sets in this power set. We're going to talk more about that later in the course again. But if you want to, you can pause this video and double check that every possible subset of set capital X is listed there. Now we have a typo here. This should say P capital X. Define a relation R on that set by saying this. ARB means that the product of the elements in set A equals the product of the elements in set B. Then that relation is an equivalence relation. So let's, question B is, find the distinct equivalence classes. So how do we figure out those equivalence classes? Well, let's make a list of these sets and find out what the products of the elements in these sets are. So there's a list of all the sets and what the products are for those sets. So we see that the distinct equivalence classes are, well, there's this one set, phi, where the product does not even exist. And then, let's see, there's a set containing 1. The product of all the elements in that set is the number 1. There are a bunch of sets whose elements, when you take their product, give you 0. Those green sets. And there are a couple of sets whose products, where the products of the elements in the set gives you -1. That's those. So the equivalence classes are these. Notice that the equivalence class is the set of all of the sets that are that have the same product, all the sets that are related to each other. So the equivalence class is a set containing sets. Now that equivalence class can go by a number of different symbols. One symbol for this big green equivalence class is it's the equivalence class of the set that contains 0. Another symbol for it is it's the equivalence class of the set that contains 0 and 1. So we see there are actually 4 different labels that work for that green equivalence class. There's only one green equivalence class, though. It's that set that contains those 4 sets. Now we've got one more equivalence class to describe. So it's this equivalence class that contains 2 sets, and there are 2 different symbols that we can use for that equivalence class. It's the equivalence class of the element that's the set containing -1. It's also denoted as the equivalence class of this set, the set that contains -1 and 1. Now let's go on. Example 3. Set A is this set of integers from 1 to 20. We're going to define a relation R on set A this way. We're going to say m is related to n means this. 4 divides m minus n. In other words, m minus n is a multiple of 4. Then that relation R is an equivalence relation. We'll discuss this in the next example. So question A is to find the equivalence classes. Now how do we find those equivalence classes? Well, let's think about the equivalence class of 1. So the equivalence class of 1 is the set of all m's in set A that are related to 1. What does that mean? Well, it means it's the set of all numbers m in set A such that 4 divides m minus 1. What does that mean? Well, to say that 4 divides m minus 1 means this. m minus 1 equals 4k for some integer k. Well, what does that mean? Well, I can rearrange it. It means that m can be expressed that way. M equals 4k plus 1 for some integer k. Now notice that that number 1 there shows up here. So the equivalence class of 1 is the set of all numbers of this form. So I'm going to move that up. I'm going to get rid of all this stuff. Actually, no, I think I'll keep it there, and we'll get rid of this sentence. We'll put that down lower. So there's the equivalence class of 1. It's just that set containing those 5 numbers. Now what about the equivalence class of 2? Well, it's going to be described the same way using a description like that. The only difference is that there's a 2 there instead of a 1 in the previous description. So there are the 5 equivalence classes requested there. Now notice that these are not all distinct. That is, this equivalence class, the equivalence class of 1, is the same as this equivalence class, the equivalence class of 5. So you see that once you get to 5, the equivalence classes start repeating. So question B makes sense now. The distinct equivalence classes will be these, just 4 of them. Let's go on. Example 4, what's called Congruence Modulo 4. We're going to define a relation on the set of all integers this way. We're going to say that m is related to n to mean this. This should say 4 divides m minus n. This is called the Congruence Modulo 4 relation. So question A is to prove that R is an equivalence relation. All right, now how do we do that? Well, remember we have to think about what an equivalence relation is. An equivalence relation is a relation that is reflexive and symmetric and transitive. So if we want to prove that R is an equivalence relation, we have to prove that it is all 3 of those things. What does it mean to say that R is reflexive? It means every element of A is related to itself. So we have to prove that every integer is related to itself. What does it mean to say that R is symmetric? It means this. For all integers A and B, if A is related to B, then B is related to A. What does it mean to say that R is transitive? It means that for all integers A, B, C, if A is related to B and B is related to C, then A is related to C. So we have to prove that R is an equivalence relation, so we'll start by proving that R is reflexive. Now, we have to write down the statement of what it means to be reflexive. For all n in the integers, n is related to n. So how do we prove this? Well, we have to start by introducing a generic particular element. So we introduce a generic particular element that is an element of the domain. Now how does this proof have to end? Well, we have to end by saying that n is related to n. All right, well, let's work backwards. What does it mean to say that n is related to n? Well, we have no choice. That's a defined expression. So we have to previously have said this. So we have to have previously said this, that 4 divides n minus n. I should make this a bit bigger. And then we can, if we have said that green statement, then we're allowed to say the red statement, and it'll be justified by the previous statement and the definition of R. So in this last line, we're packing up the definition of R. But look at that thing that is the green statement. That's a defined expression too. So we have to previously have said this. So to say that 4 divides n minus n means this. N minus n equals 4k for some integer k. So we have to have that black statement there in order to get to the green statement. Once we have the black statement, we can say that it's the green statement's true by the definition of divides. So there's the gap we need to bridge. We need to have this equation, n minus n equals 4k. Well, we don't know what k is, but we do know what n is. We've got n introduced. So let's start by building the left side of the equation. Okay, so we can say that n minus n equals 0. Oh, look at the gap we've got now. We've got to be able to say that n minus n equals 4k. Well, let's write a little bit more on line 2. We know that we want to be able to say n minus n equals 4k, so on the line 2, we're going to say that n minus n, which is 0, can be written as 4 times 0. So look, all we have to do now is introduce the k and point out that k is an integer. So there we go. Now we're ready for the black statement. That'll be numbered 4. And the green statement is going to be numbered 5. And the red statement's going to be numbered 6. And that's the end of our proof. So that's the proof that the end of our proof that R is reflexive. Now we have to prove that R is symmetric. Let's do that on the next page. Well, let's remember what the statement that R is symmetric is. The statement that R is symmetric is this universal conditional statement. For all integers, a and b, if a is related to b, then b is related to a. Well, how will a proof of this have to go? We have no choice. It's going to be a direct proof. We have no choice but to introduce a generic particular element, elements of the domain that satisfy the hypothesis. And we have no choice about how this has to end. We have to end with that. Okay, well look, we have some defined expressions. A is related to B is a defined expression. B is related to A is a defined expression. So so we have no choice about what has to come after step 1, and we have no choice about what has to come before the final step. So in these first two statements, we're unpacking the definition of ARB. And in these last two statements, we're packing up the definition of BRA. Oh, but now look, we have a defined expression there, and we have a defined expression there. So we have no choice about what's going to follow statement 2 and what's going to have to precede this second to last statement. So in statements 2 and 3, we're unpacking the definition of divides. And in these final two statements, we're packing up the definition of divides. Notice something. In statement 3, I used the letter K. So in this statement down here, I couldn't use K again. I had to use another letter. So that's why I used a J. Now look, we have a gap to bridge. We have to get from there to there. We know that A minus B is 4K. We need to be able to say that B minus A is 4J. Oh, well, this is pretty simple now. We know what we should do. We need to manipulate the equation in 3. So we just multiplied both sides of that equation by -1. Now look how close we are to where we need to be. We need to bridge that gap. So we need to be able to say that B minus A is 4 times some number, so that's an integer. And there we can see very clearly how to bridge this gap. We just have to let J be -K. And we've bridged the gap. We can now number our black statement. and our green statement and our red statement. And notice that in this proof, we had no choice about the frame of the proof, it's direct proof. We had no choice about the green statements. We were unpacking and packing up those defined terms. We had no choice about these black statements. We were unpacking and packing up those defined terms. All that we had to do that was clever was this little middle part of the proof. So we've proven now that R is symmetric as well as being reflexive. Now let's go on and prove that R is transitive. So there's this statement of transitivity. For all ABC, if A is related to B and B is related to C, then A is related to C. Well, so we'll prove this with a direct proof. So we have no choice but to start with this generic particular element, elements that satisfy that are in the domain and satisfy the hypothesis, and we have no choice about how the proof has to end. Now I'm going to streamline this a little bit. Notice in the previous proof, we used the fact that A is related to B to eventually get to this, A minus B equals 4K. I'm going to skip this intermediate step, this green step. So I'm just going to skip that step where I use the division symbol because we know where it's going to get us. We're going to know that the fact that A is related to B means that A minus B is 4K. And similarly, at the end of the proof, to know that A is related to C, it means this. So we need to get to this. A minus C is 4 times some integer n. Up here I had made a mistake. B minus C is 4m. I need to make sure that I keep that m as an m. Now how do we bridge this gap? Let's work backwards from this green statement. So we need to get to that black statement. Now let's work forwards from the green statement up above. So the green statements can be rearranged to say that A equals B plus 4K and B equals C plus 4M. Well, look, we need to get to this equation, so we've got this gap to bridge. How do we bridge that? Well, the trick is to substitute B into there. We're going to substitute all of this stuff into that equation. So now look at our gap. We have to get from there to there. Well, look, we've got C and A, and here we have 4n, and up here we have this junk. So clearly we just need to write this junk so that it can play the role of the 4n. So we introduce n, we say n equals m plus k, and we point out that n is an integer. And then we've got it. We've got that A equals C plus, well, I guess we don't even need to write that. We can just go ahead and wrap this up. We can number our black statement as statement 6, number our green statement as statement 7, and number our red statement as statement 8. There's our proof that R is transitive. So let's go back. Our job was to prove that R is an equivalence relation. Well, we can wrap up that proof now. It would be good to have a conclusion. So R is an equivalence relation because it's reflexive and symmetric and transitive. Question B, describe the equivalence classes. Let's go and do that on that last page. So an equivalence class for a number a is the set of all b's such that a is 4k plus b for some integer k. Well, this can also be written the following way. I can just multiply that previous equation by -1. I can just rearrange it and get this. B equals 4j plus a. I like this version better because it has the a on the right side. So the equivalence class of some number a is all of the numbers b that you can get by doing this stuff to a. Build an expression 4j plus a where you have some integer j. So what are the equivalence classes going to be? Well, there's going to be the equivalence class that contains the number 0. That equivalence class is this set containing an infinite set of integers. They're all multiples of 4. Notice that that equivalence class can be denoted by different symbols. All those symbols are valid symbols for that equivalence class. We could also use the symbol, the equivalence class of -4. Now there's another equivalence class, the one that contains the number 1. And that goes by different names as well. There's another equivalence class, the one that contains the number 2. And that goes by different names. And finally, the last equivalence class is the one that contains the number 3. So there are just those 4 distinct equivalence classes. Now, based on our observations about equivalence classes, the following definition of the representative of an equivalence class makes sense. Suppose you have an equivalence class called S, an equivalence class for the relation R. What's called a representative of class S is any element little a such that the equivalence class of A is the equivalence class that we're talking about. So for instance, in this previous example, consider this equivalence class. That equivalence class can be denoted by any of these symbols. So one representative of that equivalence class could be the number 0. Another representative could be the number 4. Any number that's in that set can be called a representative of that class. So an equivalence class can have a bunch of different representatives. Any element that's in the equivalence class is qualified to be called a representative of that class. Let's go on. These lemmas and theorems from the chapter make sense. I won't discuss the proof. Suppose you have an equivalence relation on set A, and little a and little b are elements of set A. If A is related to B, then the equivalence class for that element A is exactly the same as the equivalence class for element B. What you have to make sure that you have straight here is that this is not saying that A and B are equal. A and B are elements of the set A. They are not necessarily the same element. They're just simply elements that are related. But their equivalence classes are equal. That lemma is used in the proof of another lemma. If you have a set A and you have an equivalence relation on A, and little a and little b are elements of A, then either their equivalence classes are disjoint, that is, they don't intersect at all, or the equivalence classes are equal. Well, that lemma is used in a proof of this cool theorem, the theorem about the partition induced by an equivalence relation. The theorem says this: if you have a set A and you have an equivalence relation on A, then the distinct equivalence classes of that equivalence relation form a partition of the set A. That is, the union of all the equivalence classes is all of A, and the intersection of any two distinct equivalence classes is the empty set. So let's think about the equivalence classes of the congruence modulo 4 relation. The union of all those equivalence classes is the whole set of integers. Look at these sets we got. Those four equivalence classes contain all of the integers. But also notice that the intersections are empty. Let's go back up and look. This green equivalence class and that red equivalence class don't share any integers. They're disjoint. And if you look at this collection of four equivalence classes, they're mutually disjoint. So this theorem makes sense, the partition induced by an equivalence relation. Now what we just did with the relation in the previous example, congruence modulo 4, this relation on the set of integers where we said that two integers are related if 4 divides m minus n. That was called congruence modulo 4. Well, that can be generalized to congruence modulo d. So the congruence modulo d relation, those words are used when d is a positive integer. It means a relation on the set of integers defined this way. Integers m and n are related means that d divides m minus n. There's some additional terminology and notation. These words, m is congruent to n modulo d, written this way. We use this triple equal sign. We say m is congruent to n modulo d is the way it's spoken, and this is the way that this symbol is written. And what it means is m is related to n. That is, d divides m minus n. Now, based on what we did in the proof of congruence modulo 4 above, you can see the proof would be the same for congruence modulo d, that it is an equivalence relation. And the distinct equivalence classes are these, starting with the equivalence class of 0, then the equivalence class for 1, and so on up to the equivalence class of d minus 1. Remember that for the equivalence classes for congruence modulo 4 were these four classes, starting with the equivalence class of 0 and ending with the equivalence class of 3. Now, what about the equivalence classes of the congruence modulo 2 relation? Well, that would be these equivalence classes. Just those two distinct equivalence classes. Notice that the first equivalence class is the even integers. And the second equivalence class, the equivalence class of the number 1, is the set of odd integers. Let's go on. In our final example for this video, we'll consider expressions involving the congruence modulo d symbol. And so in this example, we just simply explain why each expression is true or false. Well, this expression is true. This expression means that 5 divides 13 minus negative 2. But that means, and we can see that that's true because we can write this equation. There's our green 5. So we can say that 13 minus 2 equals 5 times some integer. This symbol is actually false. Because minus 17 minus 7 is equal to minus 24, which is not a multiple of 5. Now how about this expression? Is that true or false? Well, let's just see. What's 13 minus 2? Now, can we write that as a multiple of negative 5? Yes. So we say that this is true because (13 minus -2 is a multiple of -5. What about question D? Is that true or false? Well, we have to investigate the difference. We can see that this is true. So 0 minus 15 is a multiple of 5. Now what about this one? Well, we have to investigate 15 minus 0. We can see that 15 minus 0 is also a multiple of 5. All right, what about this one? Well, we have to investigate 0 minus 0. Well, 0 minus 0 is 0, and that is a multiple of 5. So since 0 minus 0 is a multiple of 5, we can say that that's true. Now what about this last one? Now notice that I can write the following equation. So 0 is a multiple of 0. But the thing is, when you go back up and look at the congruence modulo D relation, the thing that's playing the role of D has to be a positive integer. So this is not allowed. We cannot have this symbol with D being 0. So even though this blue equation is true, this symbol is false. So that's very important. Maybe I should move this over. So even though this equation is true, this statement on the left is a false statement. All right, that's the end of that example, and that's the end of this video. Thank you.